Section 1.4, Objective 2, the velocity problem. The student will understand the problem of finding the velocity of an object at an instant. Suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above the ground. Find the velocity of the ball after 5 seconds. Okay, so we're way up there, drop the ball, 5 seconds later, how fast is the ball going? Well, through experiments carried out 4 centuries ago, Galileo discovered that the distance fallen by any freely falling body is proportional to the square of the time it has been falling. This model for free fall neglects air resistance, so wind doesn't count. If the distance fallen after t seconds is denoted by s of t and measured in meters, then Galileo's law is expressed by the equation s of t equals 4.9 t squared. The difficulty in finding the velocity after 5 seconds is that we are dealing with a single instant of time, t equals 5, so no time interval is involved. If a time interval were involved, then we could just find the number of meters traveled, that is the change in the position of the ball, and divide it by the amount of time that has elapsed, and we would have a velocity. That would be rate divided by time. I'm sorry, distance divided by time. However, we can approximate the desired quantity by computing the average velocity over a brief time interval of 1/10 of a second from t equals 5 to t equals 5.1. So we can't quite get it at the instant that t equals 5, right exactly at that 5-second mark, but we can again start to approximate. Average velocity is change in position, in other words distance, divided by time elapsed. Okay, we know that, right? We know that d equals rt, and divide both sides by t, and r equals d over t. The rate that is velocity or speed, they're all the same thing, equals distance divided by time. Change in position is the distance divided by time. Now, this is the average rate of change of position with respect to time. The average rate of change of one variable with respect to another. It's like the average rate of change of y with respect to x. In other words, it's like the rise over run, like the slope of the tangent line. Same problem. So s of 5.1 minus s of 5, and we're going to divide by the time elapsed, which is 0.1, which is 5.1 minus 5. So again, it's like a slope formula, y2 minus y1 over x2 minus x1. And s of 5.1 is 4.9 times the square of 5.1. And we're going to subtract 4.9 minus the square of 5. That'll be the change in position. We'll divide it by the time elapsed, which is 0.1. And so an approximation is 49.49 meters per second. Well, again, we're going to be able to do this sort of approximation for a lot of different amounts of time, not just 5.1. Okay, so here's the 5.1 that we just did, and the 49.49 average velocity in meters per second that we just got. But now what we can do is let that time interval go from, 1 entire second to 1/10 of a second to 5/100ths of a second to 1/100th of a second to 1/1000th of a second. It's going to zero. The time interval is going to zero, so we're talking about an instant. And average velocity, well, it looks like it's approaching 49. It appears that as we shorten the time period, the average velocity is becoming closer to 49 meters per second. The instantaneous velocity when t equals 5 is defined to be the limiting value. Okay, we're taking a limit as the length of the time interval approaches 0. That limit appears to be 49. Limiting value of these average velocities over shorter and shorter time periods that start at t equals 5. Thus, the instantaneous velocity after 5 seconds is 49 meters per second.